All right, we're going to start talking about exponential growth and decay. We've mentioned this in passing, and we mentioned it in our sequence and series, but we're going to take it one step further today. Exponential growth and decay as it relates to word problems. And again, we did touch on these from time to time, but we didn't expound real deeply on these. So I've got a little formula sheet for you, and we'll follow through the notes. But the first thing we're going to take a look at is the nature of these certain functions. So as we look at exponential functions, and we're trying to distinguish, between growth and decay. Growth and decay is basically how it relates to the x-axis. If something is decaying, its value of y is neither shooting up or down, but it's basically falling to a certain amount. I like to think of it like a heart rate. A heart rate of a decay is kind of like flatlining. You have this heart rate that's going through here, and as long as it's up or down, you're okay. But once that thing flatlines like that, you're not in good shape. That's a decay situation. Decay and growth have nothing to do with their direction, whether it reaches upward or downward. It's just the behavior as it continually moves right. Is it decaying towards an amount? Like I said, is it flatlining as far as the heart rates go, or is it skyrocketing up or skyrocketing down would be growth. The thing that gets a little confusing is growth in a negative fashion is still growth. All right, so as we look at these functions we've got going here, the first one that we see is this function is starting from the top and it's going to the bottom. And then it is, like we were talking about, just dying out. Its activity is decaying. It's no longer shooting up. It's no longer shooting down. It's basically falling to one value as it moves to the right here. This is an example of a decay situation. On the example you see on number 6, you see that we started with a flat line, but as we move right, we have this action of jumping forever up. So this is an example of exponential growth. And then number 7, you can see this function is going down, and then it is decaying. Its movement is basically dying down, just like we see there, and it's ending at this point. This is an example of decay. Now I'm going to just freehand graph one that is probably the most commonly missed one, and that is this type of behavior. As we move to the right and then it dies down this way. Well, that it is an example of growth. This action is not dying down, it's growing. It's just growing towards the negative. Basically, you can ask yourself, it's growth if it's reaching to positive infinity or negative infinity as you move to the right. If it is sticking to one value, like this value is sticking to 3, this value is sticking to a y value of 0, that is an example of decay. You know, I gave you the examples when we first talked about like an airplane and a submarine. An airplane's trip starts by going this way, submarine trip starts by that. The end of the trip for an airplane, the decay, is landing, and the end of a submarine is submerging to the water there. So this is what they look like. Don't worry about negative or positive. If it's reaching to one of the infinities, it is growing. Now, the way we determine if a function is, an exponential function is growing or decaying, is completely based on the base number. So let's highlight our base number. Our base number is the number that the exponent is attached to. So we see these numbers here are all the ones that are attached to our x values. That's what makes them the base, and they are the ones that determine whether the function is exponential growth or whether it's exponential decay. So let's talk about when we have growth. We have talked about this before. We have growth, when the exponent, the base value is greater than 1. or we also have it if it's less than -1. That is a growth in a negative fashion, though. So greater than 1 or less than -1. That's when we have our exponential growth. And we have decay when the base value is greater than 1, excuse me, greater than -1, and less than +1. So it's got to be between -1 and +1. I hesitate to say fraction because 5/4 is a fraction, but it is a fraction that is higher than 1. If you're not sure, put it in your calculator, see if the value comes out to a number higher than 1. But we are basically looking for a value that is between -1 and +1 to distinguish if it's decay. Notice 1 is not a part of either equation because if we have a base of 1, nothing is changing. So it's not really an exponential function. We've talked about this as well. If I have 1 to the 12th power, I've done nothing because 1 to the 12th power is 1. So there's no equal to 1 because we don't care about any of that. All right, so as we look at these, all we're going to do is identify if they're exponential growth or decay. The base number for the example number 8 we have here is a value that is greater than 1. Notice I don't even care about the number in front. All I care about is the number that is attached to the exponent. In this case, that's 7. So this is exponential growth. Example number 9. Again, the base value is 0.25. We don't care about 3. It doesn't have any bearing on whether we have exponential growth or decay. This is a value that falls into the between 1 and -1. So this is an example that is decay. Moving to example 10, 3/4. 3/4 as a decimal is 0.75. That is a value that is between -1 and 1. So this is another example of decay. And then the last one, this is why we stay away from saying a fraction, because 5/3 is a fraction. But it is a fraction that has a higher numerator than denominator. So technically, this is 1 2/3. This is a value that is greater than 1. Therefore, it is exponential growth. And we don't even care about the 1/2 in front. It has nothing to do with growth or decay. It just has to do with where we are going to start. Hopefully you'll find this sheet on your thing. I would rewrite this if you're planning on keeping notes in a different way. We're going to throw 4 formulas at you. The first 2 are coming today. The next 2 will come tomorrow. But this is the formula you need to write down. Technically, you could write this in one formula, and the formula would be a sub 1, 1 plus or minus r to the t power. If you wanted to do this, you're welcome. You're welcome to do that. What we need to recognize in all of these parts, and you can call this a sub 1. It's technically not a sub 1 because we don't have a sequence here, but this is our initial amount. You could call it first term, but it's the initial amount. This is where we are going to start. Money invested, where the value of a car. This is where, if no time elapses, this is where we should be. The R stands for the rate. This is a rate. Make sure you do not do this in percentage form. If you want to put a note to yourself, make sure it is a decimal. Make sure it's a decimal. And then T is the time elapsed. The same thing is true on exponential decay. Again, the only difference is the subtraction value. So we are going to have the exact same thing. It's the initial amount. R is the rate. In this case, the rate is going to be the rate is going to be a subtraction. Also needs to be written as a decimal. And then t, of course, is time. So as we look at these values, what we want to do is we want to think of it compared to our rate compared to 100%. Everything starts at 100%, and remember, 100% is not a number. It's a representation of the number 1.0, or just 1. So as we look at these things, let's go ahead and get the initial value. It's really easy to find. It's going to be the value that's in front of our base. So our initial value in this case is going to be 4. Now, it says our growth or decay factor. So our growth or decay factor in this is going to be 5.6. We're not going to be concerned too much about this number moving forward. That obviously is what's going on, but as we deal with word problems, we're going to compare it to 1. So what we essentially have here is, remember, we are based at 100% or 1.0. So we ended up with 5.6. So if we subtract 1 away from this, that means our growth rate is 4.6. So this particular equation we have here is growing 460%. It's growing 460% because we initially started at 1, so this has a rate of 4.6, which is 460%. Moving on to the next one, let's get that initial value out of the way, which is 11. The value in front of our base. Our factor is 0.4. We do not need to put the 0.40, but we start at 100% and we end at, or 1, and we ended at 0.4. What this means is we've lost 60% because we went down 0.6. So what we have is a decay rate of, excuse me, ask me the rate, so this would be 60%. Notice I circled decay, and I do not put a negative number. By saying decay, I'm letting you know that I am going to subtract 60%. Number 14, the initial value. Well, there's nothing in front of the fraction, but it's never nothing. Remember, we always have an understood 1. That's not an uncommon thing either, so this one is 1. We have a decay rate, because this is a number that is between -1 and 1, so it's 1/4. Well, if I was at 1 and now I'm at 1/4, that means I've lost 3/4. 3/4 is 75%. And again, we don't put negative, we just recognize that it is a decay of 75%. All right, so let's take a look at this world population question. It says in 2000 there was approximately 6.0 billion people. The annual rate of increase is 1.62%. As we said, we always start at 100% and we move from there. So if this is 100%, what we're going to do, we'll write this as a 100% to start, plus the 1.26% puts us at 101.26%. What we've got to remember to do is to move our decimal place over, because this is not a number, this is a representation of a number. So we're going to move our decimal place over 2 times. So our answer to the question, the growth factor, is going to be 1.0126. So that is our growth factor. Again, everything is based on 100, and this is the middle of the formula, 1 plus R. We just got to remember that 1 stands for 100, and R needs to be written as a decimal. Suppose the rate of increase continues to be 1 0.26%. Write a function to model this. Well, this is where we go to our little formula we have there. We could have written f of t, but we'll just leave it as y equals on this. So the starting amount is 6.08 billion. Now I'm going to go to my other side here and make sure that I recognize 6.08 is in billions. I don't want to come away and think that the planet has 6 people on it. So my rate is 1 plus, but we've already calculated that. So I'm going to go ahead and write this in here. You don't have to exactly write the formula the way it is. You just have to make sure you use the formula. So this is our base amount, 1.126, and we have an exponent of t, which is in time. And this did tell me that it was compounded annually, so it's only happening once during the year. We'll talk about what I mean by that a little later. So this is our answer to our function model. And then the last thing you'd ask me is, let x represent the number of years past year 2000. We use t, so we're going to go ahead and change that. We can change it in our formula either way, as long as you're comparing the appropriate things. So we'll call this value t and x. There we go. So all we're going to do is basically take our function to our calculator, 1.0126. So when we get to this point, it's very important that you think about what your exponent is going to be. We're talking about the year 2000 to the year 2010. Well, if that's the case, then 10 years have elapsed, so this value would be actually 10. Now, I'm always very nervous when I do these, so one thing I do is I take it to my y equals, and I type in my equation. That way I can look up the year that I'm interested in. I'm not going to look up 2010. What I'm going to do is set this equation where I recognize that zero is the year 2000. So I put this in and I look at my table and I see what year has the 6.08. And if you look at your table, you can clearly see that it is 6.08. So that means that's set for the year 2000. I've never been real comfortable when I was working on these on making sure I had the right thing. And then I look down the table, and on the 10th value, what we get is 6.891. So what we've learned is that in the year 2010, based on this data, obviously that's 12 years ago, we should have had 6.891, and then we look back and read billion people on the earth. So that's how we use our exponential function, and this one was a growth. We're going to take a look at a decay as well. So here we have a computer that has a value of $6,500, depreciating 14.3% every year. We need to write a function model for this. We're actually going to write the longer one here. What we have as well, we'll just call it f of t. T is going to be the variable we're going to use. Well, it has a starting amount of $6,500. And this is a depreciation. Depreciation is another way of saying decay. The value is going to get lower as we go. And I'm actually going to put it in my calculator this way as well. But we have minus, not 14.13, but remember we got to move that decimal place over 2 times. So it's going to be 0.143 to the t power. So this is how we create our model. Again, I've always never been confident in reading these things correctly, so I just say it to myself in my head. So year 0, I took this to my y equals, by the way. Took this directly to my y equals. Obviously, I had to use x, not t. And then I look at the table, and here's what my table says. 0 equals 6,500. 1 is 5570.5. 2 is 477.3.9. And then the one we're looking for is the third year, or at least we think we are, 4091 and 20 cents. So here's how I say it in my head. Maybe you won't have the same struggles I do, but after year 0, that would be the current year. So, okay, that's after year 0. After year 1, we're here. After year 2, after year 3. So I have to make this mental note to myself. Maybe you don't have these same struggles, but I do, because the question may say in year. Well, if we are in year 2, in year 2 would actually be this, because this is after the amount. So it's very important that you read and see that you're answering the question that's asked. So I did answer the question. So after 1 year it's here, after 2 year it's here, after 3 year it's there. During the third year we would have to go by this amount. But after 3 years we are looking at a computer that's value is $4,091.20. It may be more than that. I'm actually going to put that in because my calculator may have rounded on me. Let's just make sure. We don't want to cheat anybody on any pennies here. Good thing I did check, because when I looked away from my calculator, it ends up being 0.248, which rounds up to 249. So we're off by a nickel. So you may be thinking, well, that's not a real big deal. That it's not. It's just a nickel. But when it comes down to it, your books, if any of you do get into accounting, have got to match. So the nickel is a big deal. Not that it's a nickel, but that your numbers don't match up like they're supposed to. So this would be our answer, $4,091.25. I have a Delta Math created for you. Make sure you do read the instructions. It has things like make sure we use T as a letter. If you use the wrong letter, it's actually going to count it wrong. Make sure that you round the appropriate way. And most of the rounding makes perfect sense. If you're talking about number of people, you can't have a portion of a person. So read your instructions and good luck.